Hello, this is Jun Cowan here. Today I want to discuss something very important in the mining industry, that is structural data from core. There are a lot of articles on this topic and I can show you a few of them. Here's one by Brett Davis, which was published back in 2014. The original articles were actually blog posts in 𝗿𝗏𝗏. They can be now found in structuralgeology.com under blog. So you can go there and find his 3-part article. 2020, an article by 𝗃 geologists. That's one of the most recent ones. And then there's the most recent one by 𝗿𝗏𝗏 on his consulting website. You can go there and grab this one too. And this one is quite comprehensive. Now, there's a lot of information like this, how to measure structures from core, but there's hardly anything written on what to do with that data. I just want to outline some of the really basic things that I do when I look at the data. I want to discuss something that is really important, and it's the way you display the data in a Stereonet. Okay, this is something that people have not really thought about for the last few decades. So what I'm going to do is, this is going to be a rather long introduction showing the types of Stereonet plots that have been made in the past, going right back 100 years ago, and then look at what's been happening recently. And there is a shift that has happened recently. So I want to point that out. And then discuss what I've come up with. And what I've come up with is summarized in this paper by myself and Bruce Hobbs. This is about Perkins discontinuities. I won't discuss that right now, but something that is really important in here is the use of rotated Stereonet grids. So this is your typical meridional grid, okay? It's just north-south oriented, and this is what's been published as a matter of routine in publications. This is a polar plot. This is quite useful. In fact, you can actually sort of use this, even draw by hand in the field and then place your measurements on this plot. So I think it's a very useful plot. Whereas this one, you can't actually plot anything with that grid. Okay, so that's, yeah, I have a problem with seeing this grid. Okay, so the one I'm using is the rotated grid. Okay, there's really no one other than, there's only one book that shows a rotated grid, a textbook. So what I want to do is to explain the benefits of the rotated Stereonet grid. I think it's the next evolution of the Stereonet plot, since what's shown here is not useful. One way of demonstrating how to use this rotated grid is to analyze whether your structural data has been rotated because of core rotation. So I want to demonstrate that. But first of all, I want to go through the history of, some of the Stereonet plots that we've been seeing over the last century or so. Yeah, so I'll do that first. And if people want to skip that bit and go to the next section, which is really discussing 4 deposits. I'm going to analyze 4 deposits, look at their structural data, oriented data, determine whether there's some rotation in the structural data by using the rotated grid, and we'll have a discussion about that. So if you want to skip to that, you're more than welcome to do that. I just want to do a quick review of what the Stereonet plots look like throughout time, and this goes back to 1930. This is Bruno Sanders' book. The Stereonet looks like this. This is the Schmidt grid, and doesn't look any different from what we use today. These are his plots. The thing to note, for you to take notice, is basically the background. So before that, he showed the grid, okay? And in here, when he plots the data, he doesn't show the grid. And that's the only thing that I want you to take notice of really, as I go through all the literature. Now, this is not a comprehensive review. I didn't go through the source literature. I'm just looking at textbooks mainly. So I'll do that. So this is the first one, 1930. So I'll quickly go through the other ones. This is a book by Knauf and Ingerson, 1938. It's called, Structural Petrology. So typically what you have is something like this, where you have the actual data clearly shown in the plot. Okay, so I couldn't find any books that had a lot of stereonets. This one jumps to 1963. This is my favorite structural textbook that I always come back to. Okay, so here you can see that when they plot the data, there's no grid. This is the only book actually that has a rotated grid like this. I haven't been able to find any literature that displays this grid this way. This would have been manually drawn, so it would have been quite intensive to actually draw this. This is very simple these days using a computer. 1971, this is a textbook just on stereographic projections, and this is actually an equal angle plot. And this textbook shows you how to use this grid and shows you different techniques, but when they plot the data itself, it's a bare plot. There's no grid underlying it, see? Okay, 1976. This is a book by Hobbs, Means and Williams. This was my textbook when I was an undergrad at Macquarie University, and Bruce Hobbs, who's my mentor, happens to be a neighbour of mine now. And you can see that in their stereo plot, there's no grid. It's just the data. This is contour data in this case. But yeah, this is quite typical of 1970s. Okay, this is a publication by Chris Wilson, who's been doing structural geology for quite a while. His plots, and in fact, they are probably his students' plots, were made in the late 70s, early 80s. If you look at the Stereonets, they are all without grids. See, they're very clear, without grids. All of them are like that. So he's just published this in 2024. But these old plots from the late 70s and early 80s, they look like this. Okay, this is the Geology of New South Wales, South Coast. It's a Geological Society of Australia publication. It is no longer in print, unfortunately. But again, these plots by Chris Powell are all looking like this. Now, there's a reason why I'm showing this obscure publication. It's because Chris Powell invented something that's new at the time. And yeah, I'll discuss that later on. Okay, so I'm sure there's lots of publications in between, but I jumped to 2007. And Twiss and Moores, and you can see their Stereonet doesn't have a grid underneath it. Okay, we jumped to 2010. This is the text by Fossen, and it's probably the most popular text at the moment. So if you look at this, you can see that in this plot here, see that? There is an underlying grid. That is new. And this is also shown here. This is new. We haven't been seeing this before. So 2010, okay, things changed 2010. This is a book that was published in 2012 by these guys. This is an excellent book. But if you look at the Stereonets, you can see the grid, the meridional grid. These Schmidt net. I forgot to mention the Schmidt net preserves the equal area, okay? And where the Wolf net, which was invented in the late 1800s, preserves angles. So your typical world map that you see published quite often is based on the Wolf net projection. So it preserves angles, but it doesn't preserve the areas. So this is why places like Greenland it looks as large as Africa, when in fact it isn't. So if you look at the other projection, you'll see the real area preserved, and Greenland is much, much smaller than Africa, for instance. So in structural geology, we use this net. It preserves the area, so you can do spatial density statistics on this plot. You can't do that with a Wolf net. Okay, we jump to 2020, and this is a book published by SEG, Reviews in Economic Geology 21. And if you look at this publication here, you can see that there's just the data, no grid underneath it, which makes it really clear to understand. This one here has your typical grid. This is the device that we used as undergrads at Macquarie University. It's a very unusual thing because most people are familiar with this grid. This is the Schmidt grid. And these were printed on paper. So if you look at the Reagan's textbook, at the back, there is a grid like this, which you can photocopy, put your tracing paper over it. Okay? So in the old days, you used to have the grid printed like this, and you put a thumbtack in the middle and used to spin the tracing paper around. Now, that is a bit confusing because the north arrow rotates around all the time. So, but in this case, what you do is to tape the, let me see, I'm going to tape the sheet of tracing paper here onto the outer rim of this device, and the grid itself moves around rather than the tracing paper. So the north is always kept in the same position. And you can see the grid on the outer frame. So if you do that, you can actually sort of measure great circles. The dip direction in this case is, here, 296. And the dip would be, you can count them from here. So you can draw the great circle like that, and then you rotate it, and so forth. You can do all sorts of manipulations very easily with this method that Chris Powell had invented. Now, this made a lot of sense to me. The rotation axis of this grid is actually vertical. These days, you can use your computer to do anything. So the rotation axis doesn't have to be vertical. And in fact, you can shift the grid in any way, and you can make use of that rotated grid. You may know me for asking really stupid questions. One of the questions that I asked in the past was, why do you digitize to create geological models? Why do you use cross-sections? How do you know VMS deposits are syngenetic? I'm going to ask another stupid question today. That is, it's about Stereonets. Whenever you open up a journal article or a textbook these days, you see plots of Stereonets, and they look like this. they have what I call a meridional grid. Oh, they look like this. This grid with the data plotted on top of it, okay? Why do you think the Stereonets have that, use this as a background to the Stereonet that has the data plotted? That's my question. Why do you think that is the case? Now, it's my opinion that this grid on a Stereonet with data has no practical use whatsoever, and the practice should be discontinued. And this video is quite long to explain my argument. Yeah, so that's what I'm going to do today. Now, I'm not going to explain what the Stereonet is. This is not a basic tutorial on Stereonets. I expect people who are viewing this video to have taken a course in structural geology at the tertiary level, or have independently studied structural geology and know all these terms that I'm going to mention. Okay, I should really explain this net, why I call it the meridional grid. You can compare this to the longitude and latitudinal lines on a globe. And, you know, this could be the South Pole and this is the North Pole. And these are the longitudinal lines, okay? Longitudinal lines. And they're called great circles in structural terminology, but they are planes of varying dips, and they all intersect at the South Pole and the North Pole. This axis, this north-south axis, is, you can call it the axis of rotation. So if you take one plane, one single plane here, and they're rotated about that line, then you get a whole bunch of different planes about that rotation axis. So this is the axis of rotational symmetry, and it's an important axis. Now these lines here, these are lines of latitude, and in structural terminology these things are called small circles because they get smaller and smaller. So the small circles like this, they're the latitudinal lines. Okay, so I'm going to explain what kind of situations we encounter in structural geology, but in order to explain this axis of rotation, which I think is very important, I'm going to explain it using planar structural data that rotate about the core axis. So I'll just show you. Well, let's say this is the drill hole orientation, okay? And this is the plane that is measured within the drill core. As you can see, the drill core axis here is contained within this plane. So we can call it, say, a tangent plane. If you rotate this core, you can see that the tangent also rotates. And this is equivalent to this scenario here, where you have rotation about the axis, north-south axis, and these longitudinal lines are represented by these various dips of this plane, this rotated plane, okay? Now, I'm going to put a line orthogonal to this tangent plane, and I'll rotate it, and you can observe what happens to this line. So if I rotate it like this with my hand, you can see that that toothpick is actually contained within a plane, approximately. Okay, so on a Stereonet, if you rotate that, like do this, if you plot that toothpick, that line on a Stereonet, it'll be a dot, it'll be a point, and it'll occur along this equator. All these dots will occur along this equator, and it'll lie on the equator, which is a plane. It's a great circle. So even though these are great circles, there is one great circle that goes through the equator like that. And if you twist the tangent plane by the axis of rotation, then you get a trace of the poles, the pole along this equator. But what if this plane wasn't exactly containing the drill hole? So the drill hole might be oblique to that. So I have a situation here that does exactly this. So that might be a bedding tangent data, or it could be foliation, and it's at an angle to the drill hole. And this is the normal line, okay, another toothpick. That is normal to that plane. Now, what happens if you rotate the drill core? See how the foliation now is horizontal, and the normal to that is vertical. Before, it was like this. It was steeply dipping. The foliation is steeply dipping, and this normal was pointing this way. It wasn't vertical. So if you rotate it like this, it becomes vertical and flat lying. Right, okay, so in a terrain where you have consistent foliation, okay, and you drill that, you'd expect consistent orientation of that foliation or bedding. But material that is drilled, okay, so it's rock material that's within the tube, during the drilling process, the torque, there will be a torque applied to that, and it'll be twisting clockwise fashion, because the drilling occurs in clockwise fashion, okay? Once you stop the drilling, the torque can twist the rock material in an anti-clockwise fashion. Sometimes what you get is that you have a foliation that is dipping consistently, but if there is rotation in the core, it twists around like this. Sometimes it can twist all the way around like this. So it's in a completely different orientation to what you'd expect. So this is what you get. You get twisting of the rock within drill core. Okay, so if I take this and spin it around, can you see that? The normal to that tangent is tracing out a cone-like shape. Okay? And when you plot that on a Stereonet, that line here, the normal, would trace out a small circle. Remember, a small circle? One of these things? So in here, that's about like, I don't know, 30 degrees. Let's say it's 30 degrees. So it's 10, 20, 30. Plotting that normal would produce a whole bunch of points along this small circle. So this is called a small circle distribution, and it only occurs when you have rotation in the data. Well, I shouldn't say that. When you do have rotation of rock material in a core, and if you are measuring, fabric that is consistently oriented, like bedding, consistent bedding or consistent foliation, and you have rotation of that rock material, then you'd expect a small circle distribution of the normals when you measure it. So I'm going to illustrate cases later on in this video. So there are two things to remember in this video, is that I'm talking about the subject of this Stereonet grid. But I'm going to illustrate how this grid really should be freed from this orientation by using this as an explanation, this rotated rock material in a core. Because that's the most immediate application of what's called the rotated grid that I use all the time. This is a fixed grid. Okay, this rotation axis on this grid is fixed in the north and south poles. That's what this grid represents. To me, this grid is not useful at all in a true practical sense. Even though the old days we used to print this in a piece of paper and we used to plot the stereonets on a tracing paper, it is completely useless in the digital world, okay? Absolutely completely useless. There's no point in actually plotting this when you have data on top of it. There's no reason to do that. In fact, it is a source of confusion. So this is my introduction to my question. Why is this grid used? Now, the grid is used because of a simple reason, and that is everyone else is doing it. And I think it's to do with the proliferation of software recently in the last 20 years. What people tend to do is that when it's programmed into software, they believe it to be somehow good. You know, it's representative of the experts that run the mining industry. That's a complete myth. You know, don't believe that just because it's in a software that it's correct. Okay? These days, you can actually write your own software using ChatGPT and other tools like Grok and come up with a much better solution. But the point about this is that you need to be able to think through the first principles of structural analysis first. And so this is what I'm going to focus on in this video, and hopefully you'll learn something from it. I think it is fundamental, actually. If you don't have the basics in structural geology, then you might want to learn the basics first and then come back to this video. This video, what it contains is basic, really, really basic knowledge that you really do need to know in order to interpret mineral deposits. I can't get more fundamental than that. I mean, it is a fundamental knowledge that you need to know. It's not as if this is optional. This is not optional. Okay, if you're running a drilling program, if you're exploring, you have to know this information. There is no choice. So, yeah, this is why this video is very long. It takes up a lot of time, but in our workshops, structuralgeology.com workshops with Brett Davis, we just don't have the time to explain everything. So I wanted to make a video that actually sort of goes through all the logic and explain what I'm talking about in terms of axial symmetry. Now, in the future, I'll talk about applying the concept of axial symmetry in the interpretation of mineral deposits, because that's another level that's more difficult to understand, but it is also fundamental to understanding mineral deposits. The difference between the meridional Stereonet grid, that is north-south, versus a rotated one is essentially the difference between world and user coordinate system. And user coordinate system has been used in the CAD world since its inception, actually. In order to design objects like cars, houses, you need to use a user coordinate system. Like, for example, here you have let's say the room coordinates here is the world coordinate system, because that is the world in which you reside. But you can see this ultrasound is being conducted on a fetus, and you can see the cross-section of the baby here. But that cross-section is not using the world coordinate system. It is a local coordinate system that is aligned to the axis of the baby. So that coordinate system is different from the world coordinate system. Now, in order to analyze the baby's condition using the ultrasound, there is no point in using the world coordinate system. The world coordinate system is actually irrelevant, right? So this is why showing the world coordinate system, this is the meridional grid, underneath the data This is this is a plot from 𝗵𝗏, and this is just so common, like everyone does it without thinking. It's a habit. You know, there is no meaning to this. You can't actually do anything with this grid. Yeah, once upon a time when we were using tracing paper, it meant something, but no longer. So in this case, you know, the eigenvectors are actually computed from the poles here. Yeah, instead of aligning the grid to the eigenvectors, which is the symmetry of the data set, the underlying grid is still shown, which is kind of, it's a bit like putting the world coordinate system, overlaying it on top of the ultrasound image of the baby. It's absolutely meaningless. Now, I explained to you what a cylindrical system looks like. This is a fold that is plunging horizontally to the north, and it's a completely cylindrical fold. You take the tangents of the fold and then you plot them on a Stereonet, and it looks like this. The poles are lying along the equator, so that's a great circle of that grid. Okay, so this is your typical meridional grid. If you have, these are the great circles here. Okay, so these are the poles. So if you have a non-cylindrical fold system, it looks like this. It's like doubly plunging in this case, and if you plot that, it spreads out away from the great circle. Okay, so this is a non-cylindrical system, but a typical geological data set looks something like this. It's non-cylindrical, but roughly, you know, pseudo-cylindrical, and the great circles look like this. Okay, if you have a plunging fold to the north at 20 degrees, then you have this, and you take the tangents, and then if you plot that, they plot along here. Now, notice that I've rotated the grid because I've rotated it with the symmetry of the data itself. So this location here, this is the axis, this is the rotation axis, okay? And I call it the symmetry axis because that is, you know, about which, that line about which all this data is rotating. Well, they're not physically rotating, but they have the appearance of rotation. These are all the great circles plotted, and these are the poles. So a non-cylindrical fold looks like this. Same plunge, 20 degrees. The location of the pole of this grid is still 20 degrees to 000. So 20 degrees to the north. The only difference is that there's a spread of the data of the poles. And this is, you know, like I said, this is typical of natural data. These are the great circles. Okay, so you can have more complicated looking folds. You can plot them up. This is a cylindrical system again. So they would lie pretty much all along, very close to the great circle, okay, the poles here. And they would all intersect at this position if you plot the great circles here. And of course, a non-cylindrical system would be spread out. So these light blue bands away from the great circle, these are in 5-degree increments. So there's a departure of plus or minus 20 degrees from that great circle. But you can immediately see the axis of rotation by just looking at the grid. So if you use the grid as a local coordinate system, you can immediately see what's happening in the data. And this is the advantage of the rotated grid in a Stereonet. You can't get a sense of this axial symmetry from a non-rotated Stereonet. You just can't. It doesn't help you just to plot the world coordinate system underlying your data. It just doesn't tell you anything. And in fact, it hinders your interpretation. And that is a major problem. You will not see the patterns you meant to, well, the patterns are there, you just don't see it, okay? Because the grid is not really helping you to interpret the data. So yeah, if you take these tangents and just compute the intersection of these things and plot them, they all plot here in the pole of the grid, which is what you'd expect. Okay, so the first case study I have is a gold deposit, and you can clearly see, looking down, the tectonic trend is roughly north-south. And if you look towards the east, it looks like this. So there is a plunge to the system towards the south. Okay, let's look at the structural data from here. Just to remind you that structural data is pretty rare, actually, because people can drill diamond holes and not orientate the core, so therefore they don't have any structural data to actually sort of present. And yeah, it's really quite important to, if you do have diamond core, be very beneficial to actually obtain the structural data. In this case, we are dealing with foliated rock. These are strained rock, and there's a pervasive foliation right through this mineralized host. I'll just turn the grades off so you can actually sort of see so these are the foliation values, okay? Okay, so they look pretty consistent, don't they? You can clearly see that these are all dipping towards the west, steeply dipping towards the west, and pretty consistent. So this is a good sign that we have a good data set where there's not a lot of rotation, although we can take a look at individual holes to see if there are any signs of rotation. Remember, if the average orientation is steeply dipping towards the west, then if you rotate that about the core axis, you'd expect some flat-lying foliation, and I don't see too many. Like it would look something like this one here. We can examine that later on to see if that is rotation, but it looks pretty good. So if we plot that on a Stereonet using the traditional technique with the grid that is north-south, that's what it looks like. Now, the eigendata that's obtained from the computation of these orientations shown here. So this is the mean orientation here. Now, so the whole point with the rotated grid is to orientate the grid to become parallel to these three axes. So I'll do that now. So now it's rotated. So now the pole of the grid aligns with this E3 right there. And this is the average orientation of the foliation that's dipping towards the west. The strike is slightly west of north. So yeah, it aligns with the grade trend, doesn't it? Straight away, you can see that. Okay, so how do we examine how do we find out whether any of this data is rotated or not? Well, the first thing you do is to, let's say we can examine this one here because that looks a bit suspicious. Now that orientation there, looking down, that is your average plunge line. So that's 62 to 082. Let's just select that data. Now what I do is to reorientate the grid relative to the plunge of the hole. So it was 62 to 082, right? So that is the plunge of that hole. Now, if there was rotation in this data, they would travel along this arc, the small circle, and a whole bunch would lie around along this area here, but you don't see that. So there is really no rotation in this data. I'll show you better examples. This is obviously a good data set, so it doesn't show what I want to show. But okay, so if you want to individually do these for each of these drill holes, then it's a bit difficult, isn't it? It's you'd have to go to each one of them and inspect the plunge line. For example, this one here, that's the plunge line, 59083, and you'd select that, and then you type in 59 and inspect that and so forth. Okay, so there's a simpler way of doing this. What you do is you have the information of the plunge line from the survey file. Okay, the survey file would have the distance where the survey was measured, and it will give you the plunge, it's usually labeled dip, and the azimuth. And then the plunge data itself, the plunge value, is negative. What you do is turn that into positive, and then you have your azimuth, and you just rewrite the text file to a lineation file. And then you just input into, your software, desurvey it, and then you have your desurveyed lineation file. So this is what I did here. These arrows here represent the plunge line directions, okay, of the holes where there is foliation measurement. So, if you plot them together, that's what they look like. Okay, so let's just examine that previous. Oh, let's just examine one of these holes. Okay. So I have both of them turned on. I'll just turn that on, and then I'm going to turn off S and plot that. And if you do that, the actual plot is there. It's right there. Okay. And I plot the S, and that's what it looks like. So the S, there's a bit of spread, but it's behaving quite well. So I don't think there is any rotation in this data. Okay, so let's forget about that and then just plot the whole lot. If I plot the majority of the plunges are going in this direction. So my grid has already orientated itself respect to the majority of the holes. So they are plunging towards the east, 60 degrees towards the east. I turn the S's on, and you can see that this is well behaved. There's a bit of spread, so there might be a bit of rotation, but I don't think so. This is, you'd expect more points to be spreading that way, but we don't see that. So this is a good data set. I can generate angular density, so I can actually show this as a angular density plot, and these are the drill plunges. So okay, so we have that information, right? That the foliations are orientated in a certain orientation. They're striking just west of north, which is very similar to what we saw in the grade. We see there. So if by eye, you can actually sort of judge that the foliation is, carrying the gold grade, which is quite an important information. We don't know anything other than that. These might be small veins. We don't know. It could be veins parallel to the foliation, for example. We can only speculate, and you have to do field work to actually sort of determine this. But I have a way of turning grade data like this into interstructural data that can be analyzed as well. So I'll just show you as a comparison. I'll just turn on the S, and that's what it looks like. S here. That's what it looks like. Okay, so these two are similar, very similar orientation, but these are completely independent data sets. That is determined from the grade. This is colored according to gold grades, and this is the foliation data. So there's a one-in-one correspondence. The good thing about this technique is that it's not influenced by core rotation, whereas this could be influenced by core rotation. So this is something that needs to be taken into account. This data set checks out quite well. I'm quite happy to say that there is really no rotation in the foliation data in this data set. Okay, case study number 2. Again, this is a gold deposit, and the tectonic trend is north-south. You can clearly see that. And yeah, if you rotate it around, look towards the east, you can see that there is a nice plunge towards the south. And there appears to be, if you look towards the north, a vague dip towards the west, okay? Like that. So my expectation is that there is some sort of fabric that is running this way. It's either a foliation or a bedding or lithological contrast. In fact, I have bedding readings from this deposit. Okay, so we can turn that on and see what that looks like. I'll turn the grades off. See, the measurements are taken from just some of the holes, and this is quite typical. Okay, so in this case, what you should do before you plot it on the Stereonet, you can just look at the data and you can see that there's some consistent foliation orientations which are westerly dipping. I'm looking towards the north right now. So you can clearly see that this is conforming with what my expectations. The grade was dipping towards the west, so therefore I expect the bedding, I should say, the bedding should be dipping towards the west, and sure enough, that is the case. However, there are a whole bunch of them that are dipping towards in the opposite direction, and they are at a lower dip angle than this. So if you rotate this fabric around by the axis, then it's going to go flat. So I used this tool before, okay? So this is the drill hole. If I rotate it about the drill hole, see that? See how the foliation is now flat lying and it's dipping the opposite direction. So something that is dipping towards the west can end up dipping towards the east at a lower angle. So yeah, that's what it looks like. So let's plot it. Okay, so this is the traditional meridional grid, as you can see here, north-south. Okay, that doesn't really sort of show us anything. It gets in the way of the interpretation, but you can see a cluster, quite a bit of cluster over here, that the poles are in the right place. That implies that most of the bedding is dipping towards the west. I'll just turn this eigendata off, and I'll turn on the grade circle. And if you turn the grade circles on, you can see that most of them are dipping towards the west, which is correct. But you can see this sort of circular distribution here. So one has to wonder what is producing this, and most likely it's rotating about the core. And I would expect the plunge of the core the drill core will be in this vicinity here. So if I turn on the Ls, which are the survey files, sure enough, most of the drill directions are plunging in this direction, and all the poles are distributed around a small circle distribution. Now, the way to actually show this is to simply center the grid on the plunge of the holes, like this. So now I can show you that the distribution of the poles are distributed along small circle distribution, and therefore we can conclude that there is a rotation about these holes. That's why you have this variable orientation of the bedding, when in fact the bedding should be all consistent. Okay, there's another thing that I like to point out. I'm just going to show the angular density of that. Okay, now I've shown the angular density of the poles of the bedding, and you can see that there's a dense clouded data here, and it has a tail going in the anti-clockwise direction about the drill hole orientation. Now, why is that? Why is there an asymmetric distribution? Why don't these poles distribute this way as well? Okay, well, thanks for getting online. Basically, what I wanted to know was, how do you get asymmetric distribution of the poles of planar structural data in drill core?
The reason I wanted to initiate this call was because there's a couple of things I wanted to explain before we may offer the official explanation that you provide in your publication. So the first thing that people need to understand is the concept of wireline drilling, which was invented in the 60s. Okay, so as the rods progress into the earth, the entire hole, of course, is not full of core. That's the way things were in the old days. They would drill a segment and pull all of the rods up and unload the core and go back down with the entire rod stream. But with the advent of wireline drilling in the 1960s, they invented the tube assembly, which is a small tube segment that is typically 3 meters that descends down to the bottom of the hole, seats in the bottom of the drill string right behind the bit, and as core is drilled, the rock is then fed up into this tube, and they've got water pressure and different ways to understand that that tube is full. Then they can't drill anymore, and they need to retrieve the core tube all the way to the surface and unload the core, and then send that tube back down to the bottom to seat back behind the bit and drill the next run. And so each core run is drilled successively like that. And the orientation tool is screwed onto the top of that tube. Since the accelerometer that controls orientation, the sensor that detects the acceleration vector of gravity, is orienting that tube, that's what's being reliably oriented every time. What controls the orientation of the rock that feeds into the tube is this little piece of metal called the lifter spring that's seated at the bottom of the tube. And so what happens is this little tapered spring doesn't allow the core to slide out of the tube as they retract the tube to the surface. So what happens is they have to pull the rod string back that holds the tube. The only way that the orientation process works is that last piece of core that's down at the bit has to still be attached to the earth at the time of this break process. Now, if the driller stopped the run of core on a fracture full of clay and that last piece is not connected and was rotating, you can't orient that. And so when we train, we train the drillers and anybody involved in the process to inspect that last piece and look for evidence of a sharp break. Mm-hmm. The other thing that's important for everybody to conceptually understand is that when they pull that tube up, if that spring wasn't there, the rock would just slide right out of the tube. And so what happens is that spring's catching that piece of core and setting it to the orientation of the tube steel that the core lives in.
Yeah.
And so that's when you can get good orientation. Now, in terms of the torque that we've been discussing, when you drill really long holes and they're like past, 500, 700, 1,000 meters depth, the top of the drill string is being rotated clockwise by this piece of equipment called the chuck that's on the drill. That's hooked up to the motor, and that's what spins it. Well, while you're drilling, the bottom of the drill string is pinned by the earth because it's got down pressure that they're pressing and spinning on. And so what happens is you get twisting, like taking a straw and twisting it. You might be 500 meters away with the chuck gripping the drill rod string and the ground gripping the bottom end. And, you think, oh, steel can't twist. Well, that much steel, you can get quite a bit of twist in that, just like you can twist a straw or many other materials. And so what happens is they need to back off pressure. And this is what we advise them to do during our training sessions, is to back off pressure and unwind that, relieve that torque somehow by maintaining rotation, but not having the bottom of the drill rod string pinned anymore. So if they back off that pressure, then it's a little bit free to rotate. But the problem with that is that they can't pull up too much pressure, because then they'll catch the core with the lifter spring and break off from the earth at the bottom of the hole. So
Yeah.
that's an issue. So what happens is this torque problem that creates anti-clockwise distributions of poles to planes on Stereonets that are symmetric about the plot of the axis of the core hole is caused by many things, but one of the biggest sources of this error is the torque not being unwound in the drill string. So what happens is, if they don't relieve all that twisting, when they pull back to brake, what's going to happen is the core is still being attached to the earth. Before the lifter spring catches it, the rods are going to rotate. And at that point in time, the tube is going to be set to the rods, because while you're drilling, the tube inside of the bottom of the rod strings is not spinning. There's this thing called the spindle bearing that allows the rods to independently rotate around that tube as the core is being fed into it. But once they pull up to brake, then the tube sets into the bottom of the rod string in what's called the barrel, right behind the bit. And that's when the torque is being released, that's when it can actually spin the tube that has the orientation tool connected to it, and then move the position of the mark. Sorry, but that's that's not as simple as I can explain it.
Okay.
And
No,
I've had to learn this stuff.
But in that case, you'd get you said symmetric, but I call it asymmetric, because you have the poles on the anti-clockwise sense if you look down the drill hole.
What I mean about when I mention symmetry is that, yes, it's an anti-clockwise distribution.
Yeah.
But if you place maybe a small circle through the mean of the population of poles, that distribution is going to form a symmetric trace around the plot.
Oh, I see what you mean.
Just in the center. And what that is that's controlled by the beta measurement. And so what happens is the beta is being distributed anti-clockwise, and the beta measurement is the angular relationship between the structural plane and the orientation line. The alpha measurement is the angle to core axis. So that's why the radius of the symmetric distribution moving anti-clockwise is constant, because the alpha is angle to core axis, and that's staying the same. That cannot be corrupted.
That doesn't change. Yeah.
That's right.
Change. Yeah.
That's right. And so, there's various other errors that can cause that. But I think what's important is for people to think about whether the distribution of poles is appearing to smear anti-clockwise and trail off and dissipate, or if the pole distribution is making a full donut kind of
an
shape.
even distribution.
And yeah, and even that will trail off as well. But if it's going all the way around, now you're starting to notice errors that aren't so much related to torque and maybe line drawing errors, drawing
Yes.
orientation lines over spun core,
Yeah.
things like that.
Yeah.
Rounding of alpha and beta measurements. There's a whole slew of things that we address in our training. This
Okay.
isn't rocket science that we're training the people. It's just getting people to be aware of what controls the process, because the tool manufacturers don't typically explain these things. They just teach people how to press the buttons, and they say, we've got internal 𝗂𝗂𝗄𝐶, everything's going to be fine.
Oh yeah, yeah,
That's
yeah.
that's
I'm
nothing.
familiar with that. It's the same with software use, geological modeling software. Great. Excellent. Thank you. So therefore, the structures are actually spread along, if there is rotation, spread along in an anti-clockwise fashion. So therefore, you have asymmetry in the poles of the foliation data, bedding data, I should say. Yep. So that's why you see this asymmetry. Now, you can see this asymmetry in many data sets. I just saw one in 𝗵𝗿𝗶𝗀𝗃 has a really good write-up on how to measure structural data from core, and you can obtain this from his website. It's up here. And you can clearly see that in this case here, there's an asymmetrical distribution of the poles. And this is exactly what I've shown you. It's an anti-clockwise distribution of the poles. Now he has a couple more examples where I really can't tell what's going on. They don't look like there's an asymmetry. There could be here, right here, because the contour data, I'm not a huge fan of contouring data on the Stereonet. It sort of disguises the patterns. I like to see the original data. So I prefer to work with raw plots like this and just color the angular density on the actual points themselves. So that's what I do here. You can enlarge them and so forth to make a pattern. This is like, if you enlarge them like this, it's essentially the same as contouring, but you retain the original data points. So I think this is quite effective. But anyway, this is a classic case of rotated structural data, planar data, that is meant to be consistently orientated, but is rotated because about the core. And the way you tell is to simply plot this with the plunge of the drill core, and you can clearly see that majority of data is doing this. Okay, so that is that. So this is pretty straightforward. Once you have your survey files plotted as lineations, and you have your bedding, foliation, and so forth saved as foliation data, you can import it into your software and then analyze it. Obviously, I have a way of actually rotating the grid, but this is, trivial actually. It's not that difficult if you get a program to program it for you, or you can just make your own software and like me and do that yourself. Okay, so this is Kate's study number 2 with a simple rotated data set. Okay, case number 3. So this is our east-west trending deposit. Again, it is gold, and looking north, looks something like this, and there's a vague sense of westerly plunging system here. Okay, so that's what it looks like. That, I would say, that probably is the down plunge direction. But anyway, let's look at the foliation data. So at this location, there are 2 foliations, okay? And I'm loading the data set for foliation number 2, so S2 in this case. S2 looks like this. Now, you can immediately see that there is something very suspicious about this S2, which is supposed to be pretty consistent. Yeah, look at this. There is pretty consistent set foliation here, but here they're consistently dipping the other way around. So there's something wrong with this data set. Could it be rotation about the core, like this one here? I don't know. Is it rotation about the core axis? This certainly doesn't look like it's rotated. Okay, that looks good, but then and this looks good too. But yeah, well, let's look at what we can see once we plotted this up. Okay, so let's see how this plots up. Okay, so this is using the traditional meridian grid that is underlying the data here. And you can see that it's a bimodal distribution, which is very strange. Let's see if I rotate I'll loosen that. Now, where does the drill, yeah, the plunge of the drill core, most of them sit between this cluster of S poles and this cluster of S poles. Remember, there's only there are two sets of foliation in here. So perhaps there are two sets of foliation, but this is supposed to be S2 fabric. So what does this mean? Yeah, it's clearly, you can clearly see the bimodal distribution with the drill core orientation in this region here. Now, this data set really confused me because you can draw small circle rings through here, and you can see that is supposed to be the distribution of where the poles should be. So it should be an anti-clockwise smearing in this direction here. But why are there two of them? This does not make sense. So I went into a consultant's report and read up on what they described, and it appears that the geologists who are doing the measure or categorizing these structures mix the S1 and S2s up completely. So they were misclassifying these. So in fact, this set, the horizontal set, which could have been explained by, the rotation about drill core, is actually an earlier foliation. That is S1. Okay, and this is S2. Yeah, it's really confusing. Okay, so just to be sure, what I'm going to do is to show you where these poles occur. So I can select these. Okay, so this is the only drill hole where there's dominance of this flat-lying material. And there's quite a few in here too. But elsewhere, it's scattered all over the place. Okay, so this cannot be really easily be explained by drill core rotation. You can make them smaller. Yeah, that's actually quite consistent. Yeah, but in other places, they flip-flop. Here, see? From the steeply dipping one to the more flat-lying one. So this is how you figure out what's actually going on here. And it does fit in this pattern of switching between, you know, S1 orientation and S2 orientation in short distances. Yeah, this supports the idea that this has been the foliation has been misclassified, and the fact that there's no sort of asymmetry in the distribution of the poles. Although there are other reasons why you can get core rotation. This is consistent with the understanding that the misclassification of S1 and S2 are mixing up. Okay, I've just roughly determined the orientation of the gold grades, and I can plot that against the S's, and you can see that this cluster here, that's the S2 orientation, it coincides very well with the visually estimated gold continuity. Now, the natural tendency to interpret this is as follows: that the grade is parallel to the S2 foliation, dipping towards the south. However, that doesn't necessarily mean that the mineralization is influenced by S2. Now, you could have short continuity of grade that is parallel to S1, but is enveloped by the S2 trend, if you know what I mean. So there are several ways of interpreting this. It doesn't necessarily mean just because you have a coincidence of the large-scale gold continuity with a particular foliation direction. That doesn't mean that the grade carrying structure is a parallel to S2. Okay, it could be parallel to S1, but the enveloping bounding surface could be right angles to the S1, you know, so you have ladder veins that are mineralized, but the boundaries are actually parallel to S2. Anyway, there's various ways of interpreting it, so you can't jump to conclusions, but this is where someone like Brett Davis comes in and looks at the actual rocks to sort of see which interpretation fits in. So I can make broad predictions about what to expect on the ground by doing this type of analysis. This is it's really useful to look at data like this. What appears to be rotated data set is really not rotated, but it's a confusion between two different fabrics. So this is something that you really need to sort of learn more about, and yeah, at structuralgeology.com we teach you that. So what about comparing the S values to the locally varying anisotropy? I've summarized the general principle in this article with Bruce Hobbs, and I use the technique extensively. So yeah, check that out. Check it out in this journal, and it's free. You can download it, and I'll leave a link in the article. LVA S values and if I plot this up, yeah, it's pretty much identical, right? Oh, I don't have the dip right there, but that orientation there is the same as that. It's virtually the same. But you can eliminate the fact that the grade is parallel to S1, which is in this orientation here. It is steep. So that's pretty clear. So yeah, so that's case number 3. a deposit, structural data that appears to be rotated, but in fact it's not. It's actually just misclassified. So this is so important to actually check your data while you're actually taking the measurement, you know, and thinking about how it should be behaving. If you have just one foliation, you have no excuse. I mean, if it's consistent, then it should plot in the same area, the Stereonet. And if you have two foliations, make sure you know how to identify the difference between the two. You know, the second foliation would be a crenulation cleavage, so you should be able to identify it. Okay, moving on. I've left the best one for the last. This is case study number 4. Okay, so this is generally north-south trending again, but these are segmented deposits, and I'm just guessing, but these are probably Perkins discontinuities that go across it. Therefore, you know, you have this segmentation, and this is quite typical of orogenic gold deposits. Again, this is gold. Let's look at the foliation orientation this time. Okay, generally, when you look at this, there's some strange things going on here. There's this twisting of, see this twisting of the data here? There's supposed to be consistent foliation. All this is consistent, you can see that. But in some places, this one here is completely twisted. Right angles. Here, very consistent. Here, what's happening here? This is also consistent, but dipping exactly the opposite direction. See this? This is dipping towards the west at a steep angle like this, and supposed to be one foliation here. Okay, and these holes here, that's really consistent, but it's has a low dip towards the east. There's something going on here. There's consistency in the orientation here, consistency in orientation. This differs from case study 3, where you get these, you know, different orientations all in the short, you know, short lengths. So here you have pretty consistent pattern there, pretty consistent pattern there. Pretty consistent pattern largely, except a couple of holes or a few holes here that are doing something strange. Okay, so what is going on here? Let's plot it. I'll plot, this time I'm going to plot the survey data at the same time so you can immediately see what's going on. Okay, so the grid has rotated to the average of everything, so we don't want to do that. We'll just click on here and rotate the grid, and you can see that majority of the data clusters around here. Let's just contour this data and then plot it. That's what it looks like. See that tail? I mean, this is a classic case of rotated core due to spin. So yeah, if you want a more detailed explanation of why core can rotate, just read some of the references that I tell you about at the list of the references. Brett does a decent job, and so does Rod Holcomb. Okay, so the funny thing is, there's supposed to be a dominant foliation. This is clearly the dominant foliation here. That's the pole here. So I'm expecting that to be the main orientation. Okay, so I'm expecting that to be the orientation, and that appears to be consistent with the grade, but we'll check that out later on. Okay, so this is twisting anti-clockwise. But what is this cluster? So let's just highlight that area to see where that is located. Okay, as suspected, only some of the holes are in that orientation. Show the foliation that's in the orientation. Okay, forget about the L's, that's not important. So these 3 holes here they have a foliation that's in the completely wrong orientation. Now, whoever did the collecting of the data here should have realized that a flat-lying foliation for this deposit should be wrong, okay? And how did they get this? Well, the twisting effect you have that I showed you, this twisting effect, this is probably due to core rotation about the axis of the plunge of the drilling. But this requires another explanation. And I suspect what it is that they mark the core, the orientation, the ori line, on the wrong side of the core. Instead of doing it on the underside, which is the tradition, they must have put it on the top side. So therefore, you have a flipping of the grade data. Not the grade data, flipping of the structural data. So that's what you end up having here. I think that is my hypothesis. I really don't know, but that is, I believe that is the case. Okay, so if you go to structuralgeology.com and go to blog, this one here. Okay, if I go down to the bottom, there is a case where, I describe a case study here where the orientation of the foliation is different depending on, where we're looking at. Yeah, in this case, the company confirmed my suspicions, telling me that the core orientation line was marked on the top of the core because of the electronic core orientation device they used, rather than the traditional convention of marking on the bottom of the core. But their beta measurements were recorded as if the orientation line was on the bottom of the core. Wow, very confusing. There was no indication in the structural table that the beta measurements are not relative to the bottom of the core, so I had to apply a default method of alpha-beta conversion to 𝗵𝗵-azimuth readings. So once I did the conversion, that's what it looks like. The rotation pole of both looks the same. These are bedding readings, by the way, yeah. So before, the plunge differed, right? There's one plunging one way and the other one plunging the opposite direction. It just didn't make any sense. We knew that the plunge was to the northwest just by looking at the data. So when we did this correction, it looks correct now. So there are so many things that could go wrong with structural data, and it's so important to check your data and plot them up and understand what you're doing before, you just leave them in the database. Structural data is useless unless you check your data as you go along. You really do need to check it. Okay, let's go back to, so what should I do? What I should do is really take out this data set here. So I'll just do that. Quickly take out. All right, so this is approximately what it should be like. So I've just only selected data that is not misclassified, okay? So it should be all striking north-south. Okay, let's look at it. There you go. Okay, so this is my LVA result. This is the grade foliation directly analyzed from the grade itself. So there is no rotation issue here. And you can see that this is dipping, the foliation is dipping towards the west. And the measured foliation, by just taking out the rubbish bits, you can see that the dip is pretty much the same. So now obviously the grade is influenced by this foliation. There's only one foliation there. So we don't know the timing of the grade, one could naturally assume that this was this mineralization happened during the foliation development, but that doesn't necessarily mean it's true. There's many case studies that I've written with Bruce Hobbs where we believe that the mineralization was after the foliation development. I don't particularly really, favor the shear zone model of gold. So it's really important to look at all the details, all the structural details, not just the hand sample scale, but at this scale, at the deposit scale. And this is really the first place to start your investigations, to look at the deposit scale if you're obviously working in a mine and want to find brownfields targets. This is the first step that you should take, and make sure that your structural data is sound before you use it. So I've given you 4 examples. One was really good. The data set wasn't, that we didn't find any rotated data sets. Okay, so the second one was clearly a rotational issue with the about the core axis. That was very clear. The third one was a mix-up between S1 and S2. This is something that you really need to sort of figure out how to do, and you can talk to us. Brett will teach you all the techniques that you need to know. And the fourth one is, it's another one. It's rotated. You can clearly see the asymmetry in the distribution of the poles. And you have the flipping of the poles, that it's a crazy situation where you get this. And this is not due to smearing. This is most likely to do with the fact that the ori line was put on the wrong side of the core. That's my guess here. Anyway, that's it. This was a fairly long video, but hopefully this will teach you a few things about why I use a rotated Stereonet grid. It is so useful, and the most obvious application of this technique, this methodology of rotating the grid, is looking at analysis of structural data to see if there's any rotation of the data. And obviously you need to use this on a structural element that is consistent throughout the area that you're investigating. So you need to have something consistent, like the bedding. The bedding is dipping in a certain direction, or the foliation being dominant, and that is orientated a certain way. That's really the only way to check it. You can't use this technique using veins or faults, because you can't really sort of understand the consistency unless you have completely consistent vein orientations. But I would stick to bedding and foliation. They're the simplest. So if you have any questions, please leave them in the comments, and I'll try and answer them. But if you want to learn all these techniques and more, you should sign up to our workshop. Go to structuralgeology.com and register your interest. And also you can write to me as well. So in conclusion, for about a century, the Stereonets were plotted in plain backgrounds. But around 2010, we saw a change, and we started to see these meridional grids in various publications, and including textbooks. Now, I argued that the reason for this is software proliferation. Software companies are adopting to put these grids on their Stereonets. I don't exactly know why, but that's what they've been doing. So you know what this means, right? It's happened over the last, 15 years or so, 20 years. Yes, we're in the matrix now. And you guys didn't even know that you're in the matrix, because it happened over such a long period of time that you didn't even notice that you're in the matrix. Now, I'm suggesting that we should be using, not go back to the plain background, but using a rotated grid, okay? Because it's really quite beneficial. I've demonstrated this using core rotation data, and this was the originally published example from the 𝗵𝗲-𝗲𝗏 deposit that was published in 2020. All the other examples are from the analysis of various mineral deposits. It is extremely useful for the analysis of mineral deposits, but there's a long way to go. I need to convince a lot of people. But who has been sucked in to the matrix? This matrix here that displays meridional grids. I mentioned before that 𝗿𝗵𝗃 was none of those people, because I could see that in one of his textbooks, published in 2010. Now, recently, 𝗏𝗏 and 𝗿𝗏 have published two excellent review papers, and this is the earlier one, published in 2021. Really brilliant. It is a textbook. You should get a copy of it. Everyone should have a copy. It's a brilliant review. But in their figure 22, they show this. This is the meridional grid in the Stereonet, okay? So what I want to do is to demonstrate, just taking these two Stereonets, and show you what these would look like with a rotated grid. Here's the original one. You can kind of guess what the fold axis plunge is. It's about 30 degrees, but you can't really read off this grid. The grid is just decoration. So after I put my grid on, you can clearly read that this is 10, 20, about 24 degrees plunge, okay? And you can also see that the data doesn't quite follow along a great circle. That's probably a drawing error. Here's a small circle example, okay? You can see that. You can't do much with that grid. Here we have the rotated grid, and you can clearly see that the theta value is 40 degrees. You can read that off. You can also read the spread of the data. You can read it off straight off this grid. So it's extremely useful grid system. So I just picked on this paper because these guys are at the top of the game. I mean, these guys are, textbook writers, they're review paper writers, they know what they're doing, okay? So I'm not really criticizing their work. I mean, if I was criticizing their work, it's like criticizing the Big Pen, okay? The Big Pen has been sold over 100 billion times worldwide. And there was a specific invention in the Big Pen that made it really, really big. A slight tweak, and that is the hole at the end of this cap. Now, this cap prevented kids from suffocation, and that allowed them to mass distribution of this Big Pen in schools. And this, of course, reduced the lawsuits, and that helped make the Big Pen the best-selling pen in the world. So just imagine this piece of work is a bit like 𝗿𝗏's work, right? I mean, he does fantastic work. I'm just suggesting a little tweak here. Put a hole in the cap. That's essentially what I'm suggesting. The Stereonet needs to be revamped. And I think the best revamp that you can do is to use a rotated grid on it, because it is extremely useful. I don't know when we're going to get there. I published this initial image in 2020 and no one really took a notice. So I just wanted to make this video to explain the benefits of the rotated Stereonet grid. It is brilliant. I'm going to show you many more benefits of this system in the future when I make some videos about mineral deposits, because it's incredible what you can do with it. It tells you a lot about the symmetry of mineral deposits and the internal fabric. So to me, I can't go backwards. I can't just use a plain Stereonet anymore. This grid is really part of my interpretation process. I have to use it. So I wanted more people to actually understand what I'm doing. Anyway, thank you very much for staying till the end of this very long hour-and-a-half video. Make sure you like my video and give me a thumbs up on LinkedIn, and go to my paper with Bruce Hobbs and have a read of that. If you have any questions, please send me an email. And if you want to learn any of this stuff in detail, you need to attend structuralgeology.com. Express your interest and then attend one of our courses. Thank you very much for that. I really appreciate your time. Thank you.